Welcome to homework.
Alright, so in this problem, we just need to calculate the number of revolutions that the rotor executes before stopping. So, first of all, let's remember that to calculate this, we should use the principle of work and energy, because we know that since this rotor is moving, we know he has a kinetic energy. Therefore, we have that the initial kinetic energy plus the potential energy generated by the force, the momentum, is going to be equal the final kinetic energy. So we just need to discover each one of these quantities to solve what we really want, which is the number of revolutions. Okay, so how are we going to manage to calculate this? First of all, we know that in the first position, the initial position, we have angular speed that is equal 3,600 rotations per minute, and that is also equal 120 pi rads per second, radians per second. Okay, so we know that to calculate the kinetic energy of rotation, K1 is going to be equal half of the moment of inertia that multiplies omega 1 square. Okay, so what is the moment of inertia of this rotor? So let's put here the moment of inertia is going to be equal m, which is the mass, multiplied by the radius square. But the problem here in this problem is that we do not have the mass of the rotor. So we need to use the weight of the motor, because we know that mass is just the weight divided by the gravity's acceleration. Therefore, we can simplify our kinetic energy and here to half omega 1 square, which we already have this, and this is going to multiply the moment of inertia. And the moment of inertia right now is going to be the weight divided by g that multiplies the radius square. Okay, so that's the equation we should solve. So first of all, let's substitute all the numerical values in here. So K1 is going to be equal half omega. Omega is 120 pi square. That multiplies the weight. The weight is going to be 110 divided by the gravity, which is going to be, let me see, 32.2, because we are not in the international system of units, therefore we cannot use 9.8. So this multiply the radius, which is just 9 divided by 12 square. Okay, so if we calculate all this, we will find that the kinetic energy is going to be equal 136.55 times 10 to the 3 10 to the 3 feet pound lb. Okay, so now that we have the kinetic energy 1, we just need to calculate the potential energy and then the final kinetic energy. So let's begin with the potential energy. The potential energy, let's put here U, is going to be described as, let me see, uh, the torque or moment. So this is going to be the moment multiplied by the difference in the angle. Actually, this should be negative because we are stopping. Okay, so since we are stopping, this should be negative, and we know that this is equal negative 2.5. Let's put in another color. This is going to be equal negative 2.5 theta. Okay, so now we have the potential energy, we have the kinetic energy at the beginning of the movement, and the last thing we should calculate is the kinetic energy at the end of the movement. So at the end of the movement, we know that our speed is zero, which imply that our final kinetic energy is also zero. Okay? Therefore, we can finally calculate what we want because the angle of rotation is the angle of rotation we can find in the potential energy. Therefore, the answer to this problem is going to be, using this first equation here, it's going to be 136.55 times 10 to the 3 minus 2.5 theta equals 0. That implies that theta is equal 54620 radians. Okay? Or for simplify, this represents precisely 8,690 revolutions of this rotor. And that's the final answer. Thanks for watching.